Okay, anyway, we'll go to that's the title. Yeah, I knew all that. So, primary school, because that's what we're really about here. Forces are two types, attraction and repulsion. In other words, pull and push, okay? Now, when you're dealing with infants and first, second class, maybe, you're not going to use words like attraction and repulsion, unless you think they're able for it. But if you are, then you've got to teach them those words. And of course, the problem is that they're not. I don't think they're actually easy words for younger children. Okay, but when you have experience of something and you're trying to demonstrate it, then you can use the words. Okay. What's the verb for repulsion? Yeah, it's a hard one. There is repulse, but it's not what you use in terms of forces. Okay. There's repel.
Oh yeah.
Yeah. You know, so there's repel. Okay. Now, in primary school, when we want to look at forces, we look at magnets, electrostatics, and simple mechanical situations. And there's that word again. I keep trying to avoid it, but it's following me all week. All right. Situations. Okay. Now, what we're going to do is we're going to spend about 2 or 3 weeks with mechanics as such, and then we're going to spend 1 week with magnetism and electrostatic, meaning static electricity specifically. Okay. Now we're going to go with a few questions, so have your clickers ready. And as far as note taking goes, the presentation will be available as a PDF from my website. The video of the lecture as the two components, the audio and the PowerPoint, will probably be a YouTube video. I don't know yet. I'll tell you. But what you should make notes on, if you are going to make notes, is not anything on the slide, because you'll have that, but it's things that I say that aren't on the slide. Okay, that would be obvious. You should only be writing like bullet points and simple concept maps, that kind of thing. Don't be writing big long prose notes. All right, but do take notes for sure. Okay, so you ready? We start a few questions. All right, and I may actually decide to skip an odd question because I've been finding I had too many, a bit tedious. All right, and we lost a bit of time at the start. The other thing is I've told the clickers to tell you if it's a right or wrong answer, but I made a mistake. So I wonder, can you spot it? Okay. So forces, strand unit of energy and forces, but also of electricity and magnetism. So which is correct? And you probably can't see there's a timer over here. No, of course you can't see. It's in shadow. But you've got 33 seconds, 30, to answer. So just to remember, you choose A, B, or C with these scroll buttons. And then, very important, is push the send button. Better hurry up, folks. The one with 2 arrows. At 10 seconds, then you will have to restart it, which will probably mean you won't get the question done. If you have any problem, as with all technology, turn it off and on again. So don't worry, it's no problem. Okay. Now, something I'd like to by the way, I don't care if you didn't manage it. You'll get some of them. You know, it doesn't matter. The problem with this question, apart from the speed, the problem with this question is the word always. All right, and words like always and never, try to avoid those when you're talking about things in science, because you know you were working towards exams when you were in secondary school, and in exams you need to have certainty. Okay, I need to know this kind of questions coming up. I need to know that the definitions I'm learning are the ones that I need to write in the paper that will get me the mark. Okay, that's fair enough. But there's a much bigger picture, and it's a much more truer picture of the way the universe is than the way you did it in secondary school. And that is that there are exceptions to many rules and laws in science. They have exceptions, and they can be broken in special conditions. All right. So always and never are not words that you should really use. Be careful with those. children will actually ask you, does that always happen? You know, and it seems very innocent. And you think, well, as far as I know, it does. All right. And I think that's a fair answer. As far as I know, it does. Or as far as I know, it doesn't. Okay. You don't have to be absolutist, so you don't, about answering questions. You don't have, you're not, your role is not this walking encyclopedia or this kind of pestering know-it-all, you know. You're to try and facilitate the children to learn. If a child asks you a question and you absolutely haven't got a clue what the answer is, well, why are we investing in ICT in the classroom? Ask them to go find it out, you know. Don't feel you have to know the answers to everything. So that's the problem with the first one. The second one there, force the same as energy. Energy has something to do with forces, yeah, a big thing. But it's not the same thing, okay? And forces can be measured. That's very important, all right? They're not some vague thing that you can't actually find out how much it is. What are forces measured in, though? What's the units of forces? You sure? What are forces measured in? He says newtons. Yeah. Is there any other answer? That's okay. All right, fine. That's correct. All right, they're measured in newtons. Sometimes when I ask the question, people tell me it's joules. All right, and joules is measurement for. Sorry? Energy. It was G. It was a word ending in G or something like that. Okay. But it wasn't that. All right. Which of the following is not an example of a force? So there's one, the odd one out is not a force. Which one is it? You've got A, B, C, D on your E on your clicker. Pick one and send it. You've got 25 seconds. Now the thing is that it's B is the odd one out because it's about energy transforming or being transferred. Okay, it isn't actually a force. So I'm still kind of teasing you with this whole energy and force kind of thing going on here. All right. Now the thing is the other things that are on that list there: magnetism, electrostatics, gravity, and nuclear attraction. They're actually the really, if there weren't any people, those forces would still be there. That's a way to put it. They're what's called the fundamental forces of the universe. It sounds like something out of Star Wars, okay? But it's not. They're the fundamental forces of the universe. They are existing in nature. And they're what keeps the universe, well, the way it is, really. And, it, you know, if it wasn't for those four forces, you wouldn't have matter, any material, or you wouldn't have the planets and stars and the whole solar systems and so on. They wouldn't be like that. Okay, it'd be some other kind of universe. All right. So these four forces, A, C, D, and E, really, really important. Okay. Two of them, of course, are down at the level of particles. Okay. And nuclear attraction is down at the subatomic level, and electrostatic attraction is at the atomic and the molecular level. Okay. And that explains why things stick together. All right. Gravity and magnetism are forces on a bigger scale. So they are. Magnetism is a feature of certain materials, okay, to be attracted to each other. But gravity is where you have large quantities of matter called planets and suns or stars, and they exert this really strong force, okay. And gravity is really important, of course, because it's what keeps us in orbit around the sun, okay, and our orbit around the sun is what gives us the seasons, and you know, and because we turn on our axis, we have day and night, so we have the seasons and day and night, and the gravitational pull of the moon is what gives us tides, okay, and sometimes those tides cause floods, and sometimes they don't, you know, and tides are cyclical, you know, there's two each day. in each 24-hour period. 6 hours to come in, 6 hours to go out, and then repeat that. Okay, and that's because of the pull of the moon. When the sun and the moon act together, you get extra high tides called spring tides. And then sometimes, when the two gravities are added one on top of the other, you get things called neap tides, and they're very dramatic. As the water comes really far in, usually causing flood, and really far out. Okay, leaving the bays and estuaries very clear of water. Okay, the gravitational pull causing tides and the turning of the planet and the planet on its orbit around the sun. When we say it causes the seasons, well, yes, but what's part of that is the whole weather system and climate system of the planet. Okay, and it's like it's following almost like a program. Okay, and of course, so you don't want to interfere with the program too well. So our weather is an implication of gravity, but it's not directly caused by it. Okay. Next question: what do forces not do, though? Okay. And if you were listening, what I was saying about certain words you shouldn't really use as much in science, the answer is very obvious in this one. So it is. Just to speed it along a bit there. Who said science was hard? Okay. Well, it must be hard for some people, because they're still not doing it. Don't forget to press the send, all right? And there's always somebody who just wants to get in there on the 99%. You know what I mean? Like, they've got this kind of edginess. Look. See what I mean? There's always one who wants to do that. Okay. And you're lucky, though, because sometimes they can just hiccup and you don't get it in. Forces, they do certain things, and there's only these things they do. They make things move. And if it's moving, they make it stop. All right? And if it's moving, they'll make it change direction. And if it's moving or it's stopped, they can change the shape of it. Okay? Sometimes you can do a couple of things at the same time. All right? You can move and change the shape of something, usually by hitting into it. Okay? It suddenly comes to a halt, and you've changed the shape of somebody else's car or something like that. But the key thing is, probably in school, you were probably told that they cause things to go into motion and they cause deceleration or something like that. But put a different way, in ordinary language, they make things move and they make things change speed and they make things stop and they make things change direction. Okay. Now, I'm going to show you a number of machines, as I call them, okay, and they're common machines. This actually is a big thing. It's a jack, believe it or not, for a lorry, and it's a big. You do this if you know charades, okay? It's not a pepper seller, okay? So you've got to pick which one do you think this is. It's all in the hand action there. And you only 10 seconds, so you better hurry up. You'll not get this one because you won't have enough time. Well, you never know. 2 seconds. 1. Oh, jammy. Okay. If you said this was a mechanical screw, you were correct. All right. But there is actually a primary answer and a secondary answer to all of these. Okay. The primary answer is normally what we would call that thing if we were wanted to say what kind of machine it is. But some of these machines are adaptations of other ones. And the mechanical screw is an adaptation of a slope or a wedge. Now, when you think of slope, we think of maybe out there in the corridor we have a wheelchair ramp going up onto that other floor. All right. But how does it work? And you say, what do you mean, how does it work? It makes it easier. Okay, that's good, because that's what machines do. They make things easier. But how does it make it easier? How does it work? Ultimately, you want somebody a thing, or a person, or an object to go from a lower level to an upper level. And that means you go against gravity. Now, if before the ramp was made, when I first came here, if somebody wanted to carry something up the 2 steps, you had to actually lift it up and bring it up with you. All right? Now that means if gravity is going straight down, you're lifting something straight up the stairs. Okay? You're going directly against gravity. And that's the hardest thing you can do. What a slope does, okay, you don't go directly against gravity, you kind of cheat a little bit, you change the direction of your own force. You push it forward and it moves up. Okay? And that changing the direction of the force is how machines generally work. Okay? That is how they generally work. Let's try another one. So I won't do all of these because I find it tedious. Okay, but here we have a thing that's hanging on an old building. It's made of metal, and normally it has a rope over it. So which one do you think it is? And it may be, you know what it is, but you don't have the word in your own vocabulary for it. And that's okay, because we'll try and provide that today. Now 10 seconds. 8, 5, 4, 2. So this is a pulley. Okay. Now some of you may have put a wheel and axle, and the clicker probably told you that was wrong. Okay. Not really, because a pulley is a type of wheel and axle. Okay. It's a type of wheel. It's a wheel with a groove around the edge, and in the groove you put a rope, a chain, or a cable of some sort. Okay, so, and it works because it changes the direction of force. Okay, so if you've got a big heavy load you want to lift, you can lift it with your arms, and you're trying to pull against gravity. But with a pulley, you put a rope to it, and you bring it up over the wheel, and you pull down in the direction of gravity. You change the direction of the force that you're trying to do. Okay, and that's how it makes it a little easier. Only a little. I'll tell you a little because you really need more than one wheel to make a significant difference to the amount of force. Okay. Okay, we'll go to another one. Now, this one, you can see here, normally everybody gets this one right. It's a wheel, all right? The axle isn't in it, but it'll be a piece of wood. Okay, so I'm just going to move on because time's out. Oh, you all want to just get the answer in there, don't you? Not everybody. There's 2 people who just don't want to bother. 1 person. Okay, so that's it. Yeah, hopefully you got that right. You know, but you never know. This one's more difficult, and I'm going to leave that maybe to next week and come back on it. Okay, but this one's is good. What you got in the picture there is a flint knife. Okay, it's from Neolithic period, and piece of flint, and it's flaked so that it's got sharp edges, and it's one of these machines. And it actually okay, it could have put any knife in there. Any knife could have gone in there. Okay, a couple of people didn't get it there. Now, believe it or not, a knife is how does a knife work? You ask kids, how does a knife work? And they'll say, it works because it's sharp. All right? Yes and no. Okay? Yes and no. There's 2 things going on with knives and blades and so on. Is that, and they're an improvement on just using a flat piece of material. Okay? because they change the pressure that you can exert on the material. Okay, okay, that's fine. But in terms of forces, what knives do is the same as the slope. Okay, when you're cutting into something, okay, you want to put the force straight into the material. But what a knife does is it because it's thicker at one point, when it goes into the material, all right, the force acts on each face, okay, pushing the material apart. Okay? So they act as slope or a wedge in the door or whatever. They lift, they separate the material, and the sharpness of it allows you to initiate the separation of the material easier. Okay, but the cutting into it is because of the fact that it's a slope. Okay, so it's a small scale slope. So slope or wedge was actually the answer here. Okay, all right, that's a hard one to get your head around. And this one, now instead of this, you have a go at this. You could, instead of this, have the ring pull on a tin. All right. The ring pull on a tin. This is, of course, a bottle opener, but it's the same idea. There's one more. Leaving it to the last second here. So it's a lever. Okay, that's what this is. A lever in the sense that it's got to have a point of action. It's got to have an action where you turn something. It's turning, and it's got to have a long beam coming out behind it. So if you put, I hadn't put beam in here. You notice the answers changed slightly in this one. But if I had beam in there and you put beam, I wouldn't be too hard with you. Okay. But that's what this is. It's a lever. And say opening a paint can with a screwdriver. And I know if you don't do DIY, that's not going to mean anything to you. Or if you're pulling a nail out of a piece of wood with a claw hammer, again, that mightn't mean much to you. And that's the problem, is that in mechanical situations, a lot of them, I think, have contexts that are not really what children experience. All right, and your challenge as teachers is to try and find contexts that suit the children. Okay, that's your job. And then, of course, the other one is really abstract, is using a crowbar. And you're kind of going, I don't even know what a crowbar is, so I wouldn't know what you're talking about. But some people know what one is. Okay. Right, moving on. Okay, so what? So what's the point of all of this? Humans utilize forces using machines, and all of those things that we had there are machines. And what is a machine? It's anything that maximizes the output and minimizes the input. Now, that sounds all very technical, but so I put in another definition under that, because, so that's my own one. It helps you do the most work for the least effort. I like that. I hope you will too. Somebody said, well, could you ever get a machine that does assignments, because I can get the most work done for the least effort. And to which I said, I thought that's what you were doing already, but anyway. So machines are those things: gears, levers, pulleys, wheels, slopes, wedges, and so on. And the computer's telling me the time is up on that. All right, we'll finish that off. Now, this task it is a design and make, but it's a very simple one. It's very short. Step 1, design a simple pop-up machine, as is found in a children's book. Now, I want to see you drawing a plan, and the plan should be drawn out first. And the plan should be annotated, but it doesn't have to be to scale or anything. We will do that another day, but today it's not. This activity is for first class, and I wouldn't expect that there should be a scale drawing for first class, but there should be a drawing in which that you're able to go from the drawing to the artifact at the end of it. The second stage, you're going to use card and paper fasteners and scissors. Any other materials? Yeah, I want you to make it nice and colorful, and there's color sitting over there on the steel bin. Now, and then the third part is it's got to work, okay? So you have to evaluate it, and as part of the evaluation, certain groups, we won't do them all because they'll take all day, certain groups are going to come up and then present their material, okay? So, you clear about that? Okay. Continue. Can anybody tell me what that is? It's a gear. And what makes a gear different from an ordinary wheel? The edges. It has what's called teeth on it. Okay? It has teeth. Now what I'm going to do is I'm going to give you out a number of gear wheels. Okay? And a beam and axle pins. Okay? And the way you use these is you push the pin through the axle, through the hole, and it becomes an axle for a wheel, and you then line up another one, push it through, now, and you're going to have this kind of strange lollipop type thing. Okay? Now, normally the next stage would be I turn the thing and you tell me what you see. Okay? But I want to know what you might have worked out yourself about this. If I turn the big wheel, what happens? The smaller wheel will move. That's the first thing. The smaller wheel will move in the opposite direction. That's the second thing. And a third thing? Well, big wheel, and if it moves one complete turn, you've told me the small wheel will move in the opposite direction. Will it move one complete turn? You reckon twice. How do you know? You're guessing it's twice. It's not actually twice. And how did I know? How do I know that? I don't have to. It's actually written on it. All right? I don't have to count the number of teeth because it's actually written on it. But it has to do with the number of the teeth, because the number of the teeth is related to the size of the wheel. No matter whether you measure the size of the wheel in its radius, its diameter, its circumference, or its area, it doesn't matter which way you measure size of wheel, but we're going to go for number of teeth. And if this is a 50-tooth wheel, okay, and a 50-tooth wheel turned once, how many times will it turn a 30-tooth wheel? Not twice. You sure 1.5? Okay. Like the only information you have, folks, is what? You've only got 3 pieces of information. Piece 1, 50 teeth on the big wheel. Piece 2, 30 teeth on the small wheel. Piece 3, 1 turn. All that's missing is the 4th piece of information. Okay? Now, 1 turn is for a big wheel. You're going to have more than 1 for the small one. Okay? Now, is there anything from your mathematical experience, your maths knowledge or whatever, that would help you work out this little problem? Ratio. Tell me about that. How do you think this could apply here? It's 50 and 30.
Yeah. So 50 moves 1. And then
yes.
The ratio between 50 and 30. So
it's a ratio of 50 to 30. So 50 over 30.
Yeah.
5 to 3. 1 and... What's 5 over 3? 1 and 2/3. So this wheel should turn 1 and 2/3. All right. Okay, let's do a different one. Maybe I started with a hard one. Okay. Maybe I started with the hard one. Let's start with the easiest one, maybe. And it's a tiny little wheel. The children call it a baby wheel. But anyway, okay. All right. A 50 and a 10. If this turns once, how many times does the 10-tooth wheel turn? Sure?
5 to 1.
I'm just checking. Yeah? Exactly. 5 times. Okay? And if that's the 10, and I keep that there, all right? Okay? Now this time I've got a 30 and a 10. If I turn the 30 once, how many times do I turn the 10? 3 times. Okay, so what I want you to do is to take a selection of the wheels. I want you to write down what you think will happen and then check it by doing it, by actually turning the big wheel once and actually working out how many times that other one turn. All right? So, while some people are still doing that, please take the stuff that you need. Okay? Come up and get it. A spreadsheet, and I'll let you see this in a minute. So, what have you got? Yep. What number? You've got to tell me. Is it a 50 to a 50 and a 30? So I'll just put this up on the spreadsheet. 50 to 30, and a 1 turn on the large wheel gives you 1 2/3 on the small wheel. Okay, thank you. Now, do you have anything different? You've got a 50 and a 50 and a 20. So 50 and a 20, and 1 turn on the 50 gives you 2.5. Yeah. Okay. 50 and a 10. 50 and a 10. Anybody got anything different? You've had 50 and a 20. We've had that. 50 and a 20. So I'm not sure it works. Okay. What have you got? A 50 and a 50 and a 30. Okay, 50. Anybody got anything different? Now, you could have had, instead, you all seem to plug for 50, okay? You could have had a 40 and a 20. what would the ratio of turns be? 1 to 2. Okay. Okay. So if it's 40 to 20, that's, if you like, a ratio of 4 to 2 or 2 to 1. Okay. So if 2 to 1 is the ratio of the teeth, then 1 to 2 is the ratio of the turns. It's turned about. Okay? Because we're referring, the first thing is referring to a particular wheel, and the second thing in the ratio refers to another wheel. Okay? Now that's a pattern. That's a pattern. The pattern is, okay, is you told me that when you turn 2 gear wheels, first thing that happened is that it moves the other wheel. Second thing you told me is that it moves it in the opposite direction. Now the third thing that I hope you see today, okay, the third thing is that it moves it in the opposite direction, but in a predictable number of turns. You can predict in advance what the turn will be. If you know the size of the wheels and you control how many turns you do on one, you will be able to work out how many you will get on the second one. Now that's important, folks, if you are designing something that's going to use gears. You should be able to predict how the thing's going to work. And things that use gears are road vehicles, things like some kinds of washing machines and dishwashers, because they've all got turning parts inside. All right. Various kinds of electric toys with motors inside. If they move across the floor, okay, they're going to have a little gear system inside them. Friction toys and so on. Bicycles is very obvious. They have gears. But even though we use a bicycle and we don't think about, oh, you know, I must use the such and such gear because the force I'm going to need to apply to the pedals in order to get up the hill is such and such. You don't work that out in advance, but the engineer who designed the thing originally did. He or she said, oh, you know, typically these are the kind of slopes that people are going to have to go on roads because you don't make roads any steeper. So these are the kind of gears that you're going to need, and this is the kind of force a typical person would apply to the pedals. So these gears should work. They're not random. It's not arbitrary. It's designed. Okay? Right. Now, so that would be what you've just done with those gear wheels is part of a 6th class lesson. But is it science or is it maths? It is both, but are you sure that ratio and proportionality is part of maths curriculum? Do you know that? You think it is? It is. Okay, it actually is, all right? So it's part of the maths curriculum. So you actually have to do things like ratio and proportion. One way that you could and reinforce it, you know, in addition to your normal teaching way of doing maths, is using practical hands-on equipment like what we've got here. But it's important in science because gears are specifically mentioned in the science curriculum as a way to make things move, and that we have to explore them. Okay, and that's what we're doing today. Okay, so what I need to do is just to show you these results.